Okay, folks, let's get into this term symbol business. Learning goal 6, know how to construct atomic term symbols for common atoms and ions. So as we're going to see, this term symbol, it's very analogous to like an electron configuration, but it's a little bit harder. So I like to think of these as term symbols on crack. But all the same, once we get used to the pattern, just like electron configuration, it becomes like second nature once we learn how it goes. So here is how our term symbol is constructed. First, this big capital L is our main term, and that gives us our total orbital angular momentum. And of course, that's a quantum number. I'll just say Q number. J gives us our total angular momentum quantum number. Total angular momentum quantum number. So the L was orbital. This is just our angular momentum quantum number. And this whole term 2s plus 1 is our multiplicity. Multiplicity. So that is our spin state. So as we'll see, each of these values, capital S, capital L, and capital J, all have a set of rules. So let's go for it. So we first remember that in the case of our subshell designation for little l, we have to remember the SPD, FG, et cetera, values for their corresponding numbers, 0, 1, 2, 3, and so forth. So all of the possible values of big L are given by what's called the Clebsch-Gordan series. And I'm going to present this Clebsch-Gordan series, but I don't like it as much as this alternative approach that I have at the bottom of the slide. But all the same, we'll go through both. So the Clebsch-Gordan series says that we sum up all of the individual values of our electrons. So for example, if we have 2 electrons, my total L would be little l1 plus little l2, little l1 plus little l2 minus 1, all the way down to the absolute value of those differences. And once we sum up those differences, we would then ascribe a letter to that corresponding number. And it matches the same as our little l value. We just use capital letters instead of lowercase letters. So when big L is 0, we give it a big S. When big L is 1, we give it a big P, and so forth. Okay. So there's an alternative approach, however, if we already know the electron configuration. And the alternative approach is given by summing up all of the individual ML values, which requires us to kind of relearn the periodic table somewhat, depending on how we might have learned it before. So for example, the ML values can be mapped out on the periodic table in the following way. And if you do it this way every time, you'll be able to get this alternative approach every single time. So for example, S only has one ML value, it's 0. P, we're going to go -1, 0, +1. With D, we're going to go from the negative values to the positive values. And with the F, we're going to go from the negative values to the positive values. Now, you might be guessing, well, there's 6 positions for P, but you've only indicated 3. And that's right. That's why we're going to really, when we put together these ML values, right, in order of the periodic table, it's going to go -1, -1, 0, 0, and then +1, +1, which is going to give me my 6 positions. We can do the same thing for the D. So we'd say -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. And that would give me my 10 positions for the D orbital. So for example, if I look at this carbon situation and we do the Clebsch-Gordan series, right? Where the Clebsch-Gordan series says we add up all of the possible L values. So you can see right away in the case of the core electrons, those are all going to cancel out. So we're really only concerned with the valence, but we'll do it all the same so you can see. So if I sum up the L's, the little L's, like the Clebsch-Gordon series tells me, I'm going to have a 0 plus a 0, right? Plus a 0 plus a 0, plus, and then now the value of L for these p electrons are 1 plus 1. So that gives me my first value. So you can see I didn't really need to add up all of those zeros, right? Because that's all going to give me 2. So my next value is going to be L plus L plus L plus L minus 1, which is going to give me 1, all the way down to L minus L. And in the case of, and it's an absolute value, so we don't have negative values, so it'll just be 2, 1, and 0, corresponding to capital D, capital P, or capital S, right? So this would be a capital D, this would be a capital P, or this would be capital S. Clebsch-Gordon series tells us all of those are possible. Well, if we do the alternative approach by summing up the ML values, and here I'll indicate the ML values below, ML for the S is 0 for the 1S, ML for the 2S is still 0, and now the MLs, as they map out here, it's going to go -1, 0, +1, right? Then now when I do this alternative approach, which is to sum up the MLs, I'm going to get the following. It's going to be, and it's the absolute value of those sums, right? So it's going to be 0 plus 0, right? I'm doing it for each electron. Plus 0 plus 0. And then now I have to say plus -1 for that electron and plus 0 for that electron. And the absolute value of all of this, I just get 1 corresponding to a main term of P. So now what about this D and S term? Well, as we might guess, depending on the placement of those electrons, right? If I had 1 electron in this -1 position and 1 electron in this +1 position, when I'm summing all those up, those would all zero out. And that would correspond to an S term. So I'll draw that picture over here. That S term would be an electron configuration that looks like this. We recognize that P term is the electron configuration that we got in that picture. And now the D term, how are we going to create that? Well, that D term could be any paired up state as long as it's paired up in the -1 position or the +1 position, right? So as it turns out then, the D and the S correspond to excited states. The P is the only one that can describe the ground state. So that's why I like this ML configuration method, because it gets us the ground state correctly each time. Okay, let's keep going. Let's now get to this value of S. And once again, we can do the Clebsch-Gordon series, or there's this alternative approach if we know the electron configuration. So the Clebsch-Gordon series says, once again, we're going to add up all of the S values like we just did, little s1 plus little s2, et cetera, where those will either be +1/2 or -1/2, depending on if they're paired or not paired. So now if we consider the case of, let's say, a singlet system, 2 electrons being spin paired. Well, one value of S is +1, the other value of S is -1 because they're paired. So that total value of S is 0. And now if I take 0 and plug it into this equation, 2 times 0 plus 1 gives me 1. Well, if I knew that it was a singlet state in the first place, I could have just said 1. It's a singlet state. That's what that means. So what if I have a doublet state? Well, I only have 1 electron, and it's arbitrary if I call it +1/2 or -1/2. So if we make it the +1/2, and now plug that value into here, 2 times 1/2 gives me 1, plus 1 gives me 2. Well, once again, if I knew it was just a single unpaired electron, I know that's a doublet state. I could automatically just write 2 for my main term, or for my multiplicity term. And now finally, if it's a triplet, both are either spin up or spin down. So that could be like plus 1/2, or minus 1/2. We use the absolute value. So S is equal to 1. When I have 2 times 1 plus 1, that gives me 3. So that's a triplet. And if I knew it was a triplet, I could have just wrote triplet automatically. What if it was a 3-electron system, all of them being spin up? Well, our big S would be 3/2, 1/2 plus 1/2 plus 1/2. And if I were to say 2 times 3/2 plus 1, so let's do that, 2 times 3/2 plus 1, that gives me 4. It would be a quadruplet. If we had 4 electrons, right, all spinning up, I would get S equal to 2, which would give me a 5, so that would be a pentuplet. So what we can see now is there is this n-1 term for our multiplicity. We're going to see it as we get more practice, okay? So finally now, to get our value of J, once again, we have our Clebsch-Gordan series where we could sum up all of the possible L's and S's. Or our alternative approach is if we got the multiplicity and the orbital angular momentum from the electron configuration, then we automatically know what J is, or what J's possibilities are. So let's go back to this case of carbon, okay? And if we recall here, for carbon, we got that the ground state has to be a P term, right? That came from adding up all of the MLs. So 0, 0, -1, 0, +1. We add all of those up, we get 1. That corresponds to P. So now we can see that both of these are spin up. So if we recognize that spin up is a triplet, we could automatically just write a 3 there for triplet. But if we're not quite there yet, if we don't recognize that, both spin up are 1/2 plus 1/2 to give me 1, and 2 times 1 plus 1 gives me 3. So now, having this triplet P, I already know what my L is, and I already know what my S is. In this case, my S is 1, and my L is 1. So I'm going to get this possibility of 3P2. I'm going to get a possibility of 3P1, and I'm going to get a possibility of 3P0. Let me keep that 3 closer to that P. So lo and behold, we get 3 possibilities for a triplet state. Well, as it turns out, we're going to see that there's another set of Hund's rules to dictate which of these are the lowest energy terms. And as we'll see, for carbon, it's the 3P0 would give me the lowest energy state. So that would be my ground state term symbol for carbon. And if you look at my periodic table right here, there it is, 3P0. This is my favorite periodic table. And lo and behold, if we look right below it at silicon, its term symbol is 3P0. Right below that, germanium, its term symbol is 3P0, and etc. So we can see the way that these term symbols map out on the periodic table. I'm going to go through a couple more examples here to really drive this home. So here are our Hund's rules, but now reconfigured to understand it with term symbols. So they're the same Hund's rules that we looked at before and in more detail in general chemistry, but now we're going to use this with term symbols, okay? So states with the largest value of S is most stable. Stability decreases with decreasing S. So this is just another way of saying if you can keep them spin parallel, or in other words, unpaired versus paired up, unpaired is better. Unpaired is more stable. If you have to pair it up, fine, but that's going to be higher in energy than unpaired, okay? For states with the same value of S, the state with the largest value of L is most stable. So if we have multiple triplet terms that can exist, maybe a triplet P, a triplet D, or a triplet S, the value with the largest L is the most stable or has the lowest energy. So for example, D is lower in energy than P is lower in energy than S, which I know is like the opposite of what we talked about for our orbitals, but remember, these are the term symbols, not necessarily the orbitals. So if states have the same value of L and S, then for a subshell that is less than half filled, this is where it gets a little funky. For a subshell that is less than half filled, state with the smallest J is the most stable. For subshells that are more than half filled, the state with the largest value of J is the most stable. So if we go back to this carbon example that we just did, carbon is less than half filled, so its smallest value of J is the most stable. Interestingly now, and we'll see this example again, if we look at oxygen, oxygen will end up having a very similar term symbol as carbon, but oxygen is more than half full, so its 2 state for J is most stable, right? So you can see that here on the table. Triplet P0 for carbon, but triplet P2 for oxygen. We'll work through this example in a moment. So now right here, if we were to rank the following terms here based on these rules, what we're going to see is the all of the triplets will be the lowest in energy, and those with the largest value of L will also be the lowest in energy. So these term symbols, it's going to take us a little while to get used to these, but it's a great way to just show quickly what our state is, and it's going to allow us to quickly look at spectroscopy data with that term symbol in mind. Okay, we'll practice these a lot during our live lecture. I'll see you later, folks.